I want to just say that I'm absolutely delighted to be officiating at tonight's inaugural address because two of the main speakers this evening, both Professor Razzaque as well as Professor Ralston, are from the University of Kansas, and it's also my alma mater. So I should say to Professor Ralston that in a period of 1 week, I've met two professors from University of Kansas, one in Singapore and one tonight. Absolute delight. The world is getting smaller and smaller. Ladies and gentlemen, it's my pleasure and privilege to welcome all of you on this auspicious and very significant occasion for the University of Johannesburg, the professional inauguration of Professor Razzaque in the Faculty of Science, Department of Physics. In particular, I'd like to welcome Professor Razzaque's wife and members of his family, and also the colleagues and friends from the Department of Physics and broadly from the Faculty of Science. I'd also like to extend a warm welcome to members tonight from our sister universities, University of Pretoria, Wits University, and many others. And to the broader public, you're all most welcome. A professorial inauguration such as the one that we will be celebrating today is a significant occasion in the life of a university as an institution of learning and scholarship. It represents the formal induction of a senior member of the faculty into the ranks of the academic professoriate. I'd just like to spend a bit of time talking about where does this tradition come from. The noun professor derives from the verb to profess, and the origins of to profess derive originally from the Latin professori, meaning before, and fatere, to confess. Thus, the original Roman meaning is to confess before the public. In the late Middle Ages, the term professor was used to refer to university teachers of the highest order and standing. While the act was no longer a confession, rather a declaration and an exposition of one's academic discipline, the very public nature of the event remains firmly entrenched. It is and always has been the opportunity for an eminent scholar to explain the principles, procedures, and objects of one's scholarly gaze to one's peers, to one's members of the public, and to one's family. The act of professing was a prelude to the conferring of the title of professorship, a title that's conferred upon very few and requires that one is famous for one's work, acknowledged amongst the universities at that time of Europe in the 1500s as being preeminent in one's particular field of inquiry. This elite group comprised the Senate, and because medieval universities were communities, the towns in which they were situated were essentially extensions of the university, providing civic services. The Senate therefore largely controlled the towns as well. Fortunately, modern-day professors do not have to function as our city councillors, although I do hope that the work that they do does contribute towards the development of our cities and nation as a whole. But there's more to this history of the professorship. The professors frequently hold chairs in their disciplines. In other cultures, the medieval origins of the chairs are Muslim as well. In Islam, the Caliph himself would appoint a kursi, which literally translates into a chair. And the kursi in the university was situated in the university or madrasa. The appointment of the kursi was for life, and the chair holder, the kursi, would sit literally in a chair surrounded by students. The kursi, like the professor, was highly esteemed, and for good reasons. Perhaps the most shining example of Islamic learning in Africa was the establishment of the University of Timbuktu in Mali in the 12th century. Many centuries ago, this seat of learning had 25,000 students from Africa and the Mediterranean. So, ladies and gentlemen, from two distinct medieval university traditions, one steeped in Islam and the other in Christianity, an outstanding academic elite tradition was established. The situation is no different today. As a leading institute of higher learning, the University of Johannesburg goes to great lengths to make professorial appointments that will ensure the status and quality of the university is maintained for the next generation. Our professors are truly significant members of our university. As members of Senate, they guide our decision-making around core academic affairs. They represent their disciplines both within and outside the university, in academic contexts and in broader professional and social contexts. They offer, importantly, academic leadership. They are also responsible for nurturing young faculty and supporting them as they mature into the next generation of distinguished scholars. All of this requires, of course, additional qualities, which we primarily associate with being a professor. It requires professors and academic leaders who also show a human face, who combine academic leadership with concern and care for their colleagues and students. And I know that this is something that Professor Razzaque does excel. Ladies and gentlemen, on that note, I'd like to welcome you all again, and to Professor Razzaque. I look forward to your address, which I know will inspire all of us. I now call upon the Dean.
Good evening. Ladies and gentlemen, it's a privilege to introduce you to Professor Razzaque by reading his CV. Professor Razzaque moved to South Africa in 2013 to take up a position at the University of Johannesburg. His primary research area is high-energy astrophysics, also referred to as astroparticle physics, and involves the investigation of astrophysical objects with energetic particles. He is also active in multi-wavelength astronomy research involving radio and optical telescopes in South Africa, such as the Square Kilometre Array, SKA, and the Southern African Large Telescope, SALT. His research group at UJ is a member of the international collaboration of the Fermi Gamma Ray Space Telescope, a NASA satellite dedicated to gamma ray observations of the sky. Prof Razzaque is also an associate member of the international collaboration of the IceCube Neutrino Observatory, located at the South Pole, and is also actively involved in the South African Gamma Ray Astronomy Program, which is supported by the Department of Science and Technology. Born in Faridpur, Bangladesh, Professor Razzaque is the fourth of 5 siblings. He studied physics at the University of Dhaka. After obtaining his undergraduate degree in physics, Prof Razzaque won a scholarship to study at the International Center for Theoretical Physics, ICTP, in Trieste, Italy, where he earned a diploma in high-energy physics in 1997. Founded by the Nobel laureate physicist Abdus Salam, ICTP is run by UNESCO and is primarily devoted to training and providing research opportunities to scientists from developing countries. Prof Razzaque started his doctoral research at the University of Kansas in the United States in 1998 under supervision of Prof John Ralston. He performed theoretical investigations of the coherence effects in ultra-high energy electromagnetic interactions with matter as his thesis topic. He also performed theoretical research in the area of ultra-high energy cosmic rays and neutrinos, and was involved in an experiment called the Radio-Aisharenkov experiment, located at the South Pole and dedicated to detect ultra-high energy neutrinos from the universe. Prof Razzaque received his Doctorate of Philosophy degree in physics in 2002 from the University of Kansas. Soon after his PhD thesis, he joined Pennsylvania State University as a postdoctoral fellow. His mentor there was Prof Peter Mezaros of the Department of Astronomy and Astrophysics and Department of Physics. During his 5-year postdoctoral fellowship, Prof Razzaque focused his research on the astrophysics of high-energy cosmic rays, gamma rays, and neutrinos. In 2007, he won the prestigious National Research Council Fellowship of the National Academy of Science, USA, and moved to the U.S. Naval Research Laboratory in Washington, D.C. He was appointed as Research Associate Professor at George Mason University near Washington, D.C. in 2011, where he remained until he moved to the University of Johannesburg. Prof Razzaque has co-authored over 1,000 articles published in peer-reviewed journals and has presented over 25 talks in international conferences. He regularly serves as a referee of top journals such as Physical Review Letters, Journal of Cosmology and Astroparticle Physics, Journal of Astronomy and Astrophysics, and the monthly notice of the Royal Astronomical Society, as well as Science magazine. He also reviews grant proposals of the National Research Foundation, NASA, the National Science Foundation, and the German Research Foundation. In his personal life, Professor Razzaque is married to Ms. Susanna Ahmed, who is an early childhood educator. They have 2 daughters. He lives in the Melville West Dean area, and other than physics, Prof Razzaque is interested in music and history. So ladies and gentlemen, Professor Razzaque.
All right. Thank you, Professor Parekh. Thank you, Professor Meyer, for the kind introduction. So this is a privilege to speak to this audience and tell about my research in a way that is conceivable to people who are not expert in physics. So I'll talk about this topic. The main area of my research is called it's a neutrino view of the sky. So what are neutrinos at the first place, and why do we care about those? So the neutrinos are very small subatomic particles, and in nature we have this atom that we all know about, and the atoms are made out of neutron, proton, electron, and we know that this is not the end of the story. There are other small things inside the atom. These are this neutron and proton are made of quarks. Electrons are fundamental, and then there are many other particles that are not shown here, but this current understanding of our particle physics is that there are quarks, these up, down, charm, strange, top and bottom quarks, and they make up the matters mostly. And then we have electrons here, and then muon and tau, these are called leptons. And then we have the force carrier particle. They communicate between the matter particles. And we all know about this photon. This is represented with this gamma. But there are 3 other force carriers that we know. It's called a gluon, which interacts between the quarks, and then W and Z bosons. They are carriers of the weak force. And then there is, of course, the Higgs boson, which has been recently discovered at the Large Hadron Collider. Now, the neutrinos, which are shown here, they are not part of this atom. Okay. Now, in many ways, the neutrinos behaves like electrons, muon and tau, but they don't have any electric charge. And because of that, they only experience this weak force. Now, this weak force is about 10 to the power minus 4 times weaker than the electromagnetic force, which is mediated by these photons. And these neutrinos, they are very light. They are less, we don't know exactly their mass, but they are less than about 1 million times the mass of an electron. And the one interesting property of the neutrino is that they mix with one another when they move from one place to another. So even if they're produced as one of these, but when we detect them, they can be another type. So these neutrinos are then part of these elementary subatomic particles that we know. But what are they good for? Well, the neutrinos are essential part of the development of universe. Now, if we look at a cartoon of our universe, so this is what it looks like. So initially, we had this Big Bang, and then we have expansion of the universe very rapidly for a fraction of a second, And then we have a soup of elementary particles, all these quarks, gluons, then bosons, neutrinos. And then as the universe cooled down, then the temperature of the universe also went down because it cooled down. And then the other particles, they can combine with each other to form atoms and molecules. And the neutrinos, they decouples from other particles from the soup around when the universe was only 2 seconds old. The photon decouples from this soup when the universe was 300,000 years old. And that is the time after this time, which is shown with this bar here. The more complex atoms and molecules, they could be formed. And as the universe evolved, more complex structures such as galaxies, stars, planets that could be formed. And we are now here at this stage of the evolution of the universe. Now, the crucial part the neutrinos plays is that they are responsible for producing heavier elements heavier than helium. Okay? So this is a process called nucleosynthesis, and through this process, heavier elements could be formed, and neutrinos also take part in this nuclear fission reaction, which powers the stars, and at the center of all the stars, there is this nuclear fusion reaction going on. It produces more heavier and heavier material, and when the star dies, many of the stars, they explode, which we call a supernova, and they throw out all these heavy elements outside, which can then be used to make new generation of stars. So through this process, we get heavier and heavier element, and neutrino is crucial for that transformation. And if we don't have if we don't have any neutrino, there will be no element heavier than helium, and that means there will be no biological element molecules, and there will be no us. So they are very crucial in the universe. Now, a brief history of neutrinos. We didn't know about the neutrinos from beginning of time. We came to know about them not very far ago, less than 100 years ago. So the first idea about the neutrinos came in 1930 when Wolfgang Pauli postulated that there should be a particle called neutrino, and it will be responsible for the conservation of momentum and energy from the nuclear beta decay. Now, in 1934, Enrico Fermi, he coined the name neutrino and also gave the theory of its interaction. But he also named the term neutrino in a way that it is different from another neutral particle known at the time. It's called neutron. So the neutron is many times, billions of times heavier than the neutrino. So to distinguish from the neutron, he invented this term neutrino. But it was not discovered at the time. Then in 1938, Hans Bethe, he calculated this nuclear reaction and showed that all stars and our sun produces light because of this nuclear reaction where neutrinos take part, and he got 1967 Nobel Prize for his calculation. The neutrinos were first discovered in 1955, so long after it was predicted. So it was discovered by Fred Raynes and Clyde Cowan from a nuclear detector, and for this discovery, the 1995 Nobel Prize went to Raynes. Now, in about 1962, this group of physicists, they discovered the second type of neutrino. It's called the muon neutrino, and got this 1988 Nobel Prize. And in 1973, Ray Davis detected neutrino from the sun. So this is the time when an astrophysical object has been detected with neutrinos for the first time. And of course, he received his share of Nobel Prize in 2002 for that. And the kind of neutrino that I'm mostly interested in, these are called high energy neutrinos. And at this energy, we can actually use them to do astronomy. And that kind of neutrino detection projects started in the early 1970s. And in 1978, there's a prediction of the third type of neutrino called the Tau Neutrino by Martin Pearl and collaborators. and it was discovered in 2000, and Martin Perl got Nobel Prize in 1995 for that. And in 1987, we detected neutrino from a supernova explosion. So this supernova 1987A is the first supernova that modern humans, in the post-civilization era, saw for the first time. And there was neutrinos detected from this supernova, and that was a groundbreaking discovery. 2002 Nobel Prize was awarded to Koshiba for that discovery. Then in 1998, two detectors, one in Canada, SNO, and the other in Japan, called Super Kamiokande, they detected what is called Neutrino Oscillation, and which is a proof of that the neutrinos possess mass for the first time, which is actually not allowed by the standard model of particle physics. So this is the evidence that there is physics beyond the standard model that we know. And just recently, last year, Koshiba, Kajita, and McDonald got the Nobel Prize for discovering neutrino mass. And in 2012, we have the first detection of cosmic neutrinos, the neutrinos that my research is focused on to learn about the astrophysical sources. So those type of neutrinos, very high energy neutrinos, they were detected in 2002 by this IceCube neutrino telescope. And now it is the dawn of neutrino astronomy that I'm mostly involved in. So far we have 5 Nobel Prizes in neutrinos, and still counting. And we have the first evidence that there is physics beyond the standard model that we know of, at least from the neutrino sector. All right, now where do we find neutrinos? Neutrinos are actually everywhere. And if we think about that neutrinos that were decoupled at the very beginning of the evolution of the universe, those are called this cosmic neutrino background. They are just like cosmic microwave background, but their temperature is a bit lower, 1.95 Kelvin, and each of us at any given time contains about 30 million of these neutrinos. Okay? Now, all the stars shines in neutrinos. They are neutrinos produced from this nuclear reaction in the sun and all the stars, and there are about 100 trillion solar neutrinos pass through us in each second. Now, a supernova produces 10 to the power 60 of these neutrinos between energy 10 and 20 MeV in just 10 seconds. That's 1 followed by 60 zeros. And then we also have the neutrinos coming from all this radioactive material. Also, these reactors, nuclear reactors produce neutrinos. We have geoneutrinos coming from the uranium and potassium in the Earth's crust. They're very low energy neutrinos. Now, the neutrinos can be used to learn something about the astrophysical sources, and that the first evidence of that we had was in making an image of the sun's interior with neutrinos. So this is how the sun looks like. So this white color means this is very hot, and then blue color means cold. So the interior of the sun is represented here with the neutrinos. That most of the energy of the sun comes from the interior. And this was done with an experiment called Super Kamiokande in Japan. All right, now we want to do astronomy with neutrinos. We want to learn astrophysical sources with neutrinos. Now, why do you need that? Well, we need to have some kind of messenger in astronomy because we cannot travel to the sources. We cannot travel to the sun, we cannot travel to the stars, our galaxies, so we have to study whatever comes to us. So we asked 2 questions with these messengers. What is there and how do they work? How the astrophysical objects work? And then we detect what is coming from us, and so far what we detect is mostly light. Of course, photons, these are responsible for this electromagnetic force. So this is the messenger in astronomy for the last 400 years, since the time that Galileo discovered the moons of the Jupiter with his telescope. And then we have cosmic rays. These are, of course, responsible for a strong force. And at the very high energy cosmic rays, also called the ultra high energy cosmic rays, they were detected in the 1960s, and in some way they could give us some information about the astrophysical sources. We have neutrinos, responsible for the response to weak force, and they're detected by IceCube Neutrino Observatory in 2012, 3 years ago. And then we have very recent discovery of gravitational wave, the force of gravity, and detected just very recently in 2015, just last year. Now, these are the different ways we can study astrophysical objects. So that's why these are called cosmic messengers. And some of them are good, some of them are bad. Of course, the electromagnetic way is the best way so far. But these neutrinos, they can also be a way to look at the universe, and that is something that I'm working on. And the first paper about this high energy neutrino I wrote when I was a PhD student with John Ralston. So we looked at a way to detect ultra high energy neutrinos, the neutrinos which carry a lot of energy, 10 to the power 15 electron volt of energy. And we did this calculation using a computer code to see if these ultra high energy neutrinos could be detected in the ice of the South Pole, and especially with the radio detectors. So that was my first introduction to this ultra high energy neutrino business. Now then, of course, I moved on and started to look at what kind of objects could produce these very energetic particles. Now, you probably all of you have heard about this Large Hadron Collider at CERN near French and Swiss border. So it accelerates particles. It accelerates protons to high energy. And this size of this is about 26.6 kilometer, and one can get about 7 times 10 to the 12 electron volt of energy from this accelerator. So this is a particle accelerator which takes up particles and move them to very high energy. And there's a power consumption is about 120 megawatt for this instrument. Now, we know that the nature actually produces much more energetic particles. So there are more powerful, fantastic engines in nature which are capable to produce much, much higher energy particles. And that's because we actually detect them on the Earth. So we detect them on the Earth. They are coming from somewhere, we don't know yet, but they bombard the atmosphere of the Earth, and we have detectors on the ground which detects the remnants of this particle, and we can reconstruct the energy of those particles. And they are over here. So they're 10 to the power 20th electron volt energy in those particles. Okay? So they must be coming from somewhere, and some astrophysical sources are probably producing these particles. So that's another reason we study astrophysical objects, to know what can produce these fantastic particles with so much energy. Now, there are different classes of objects that could produce very high energy particles. We don't know yet for sure, but we try to investigate them and understand if they can. So this is a picture of what is called a Crab nebula and a pulsar. This is the remnant of a explosion of a very massive star in our galaxy. And it has 10 to the power 45 watt of power. So remember that the LHC has 120 megawatt power. This has 10 to the power 45 watt of power. Then we have the radio galaxies nearby. These are outside of our galaxy. And they have about 10 to the power 43 watt of power in beamed electromagnetic energy. So these kind of objects are very likely to produce these extremely energetic particles that we detect on the Earth. Now, there is a rule of thumb or simple calculation which shows that what kind of object could produce very high energy particles. And this is a diagram often called a Hillas diagram. It's introduced by Mike Hillas in 1984. So what is plotted here is the magnetic field strength and then the size of the accelerator. So this is so the particles are accelerated in the magnetic field, and then this is the size of the accelerators. And this is 1 kilometer. The 1 AU is the distance between the sun and the Earth, and about 100 kiloparsec or so is the size of our galaxy. And this is the configuration you need to produce these extremely energetic particles, 10 to the power 20th electron volt. So either the magnetic field has to be very high, or the size of the object has to be very high. And then you can produce those kind of particles. So for comparison, this is the strength of the magnetic field at the LHC, so 8.4 Tesla. Okay, now the kind of source that I was mostly interested in, at least in the past, they are called gamma ray bursts, and the way they work and produce these neutrinos depend on this cosmic rays and neutrino, this shock acceleration of particles. So in this kind of source, there are plasma materials which are accelerated to very high velocities from a black hole, and then the plasmas, they collide with each other, and they produce a very high magnetic field there, and the particles in the magnetic field then can be accelerated. So this is what is known as the Fermi shock acceleration process, and the particles can gain very high energy. Now these particles then can interact with surrounding gas or photons and produce a lot of pions and kaons and many other kind of particles, and then these charged pions and also kaon, they decay to produce many secondary particles and also neutrinos and gamma rays. So from these sources, what comes out at the end is mostly these neutrinos and some cosmic rays. The gamma rays at very high energy, they cannot come out of these sources because they will be absorbed in the source. So by looking at these neutrinos and also cosmic rays, but the cosmic rays are charged particles. They bend in the magnetic field and often don't point to the sources. But if we can detect these neutrinos, then we can know where these particles are accelerated. Okay, where are these fantastic engines in nature where we can produce huge energy in particles. All right, so if we detect this very high energy neutrino, we can know where the sources are. Now, as I mentioned, these particular sources that I worked on quite a lot in the past, these are called this gamma ray burst. Now, these are flashes of gamma ray randomly located in the sky. Now, they last for fraction of a second to tens of second to minute, and they produce a lot of gamma rays in MeV energy. So, so this cartoon shows that this is the number of photons count in a detector in a satellite in space, and this is the position of this gamma ray flash. And when we have this peak of this photon count, where the flash is at the peak, then it outshines actually the entire universe in the gamma ray energy. And that's why these are very powerful objects. So we know that they are also located not nearby. They are not in our galaxy. They are in outer galaxy at the cosmological distances. So the energy of this object is extremely high. They are the most powerful astrophysical object known to us. Now, the theoretical understanding about this model so far is that these are most likely the death throes of very heavy star with more than 30 times the mass of the sun, or binary mergers up to a neutron star, or a black hole at a neutron star, and this emission comes in sort of long tube, very beamed, and this can actually accelerate particles to very high energy. So this is a cartoon of what we understand about this source. So this is a heavy star. It collapses, and then produces a black hole at the center, and then it produces jets, and this jet interacts, collides with each other, and then produce these gamma rays, and then we have very late emission of X-ray, optical, and radio from the same object, which we call afterglow. And using this model, so I did a number of calculation to see how the neutrinos can be produced here. So these are back in the days when I was a postdoc at Penn State University. So we did a lot of calculation to predict what can we expect in terms of neutrinos from these sources. And also, we can use neutrinos to learn more about the sources themselves. All right. Now, usually what the final result come out of our calculation is represented as a graph. And we, in this particular graph, this is the prediction that we made. So what is plotted here is the energy, total energy of the neutrino, and this is the energy of the neutrino in individual particles. And this is how much energy can be emitted with neutrinos of this energy ranges. Okay? So this usually looks like these lines, and the experiments can then detect neutrinos over many different energy range and try to see if this model works or not. All right, now what experiments can do that? So currently the largest neutrino detector known is called the ice cube neutrino detector. It's located at the South Pole. And this is actually buried under the ice. So the telescope is buried under the ice, and for that one needs to dig hole. So the holes are dug using hot water in ice, and these holes are 2.4 kilometer deep. So this is a picture of the hole which goes down to 2.4 kilometer inside ice. And then one puts these instruments in these holes. And after completion, this whole thing under ice looks something like this. So this is the top of the ice, and this is under ice. It goes 2.5 kilometers. For comparison, this is the size of the Eiffel Tower. So this is the cartoon of this detector. And in each of these so-called string, there are a lot of these digital optical model. These are kind of light collectors. And the way the neutrinos are detected is that this neutrino interacts in the ice or in the rock nearby, and they produce secondary particles. And these secondary particles, they go through the detector and emits light. And in detector, those these light gatherers, they can collect this light and then try to reconstruct where these lights are coming from, where the interaction took place, what is the energy of the interaction, in which direction the neutrinos are coming from, and so on. So that's the principle of neutrino detection in neutrino telescopes. Now, so far, this world's largest neutrino detector has detected 54 of these neutrinos. That doesn't sound a lot, I know. Okay, but each of them are extremely energetic. Okay, they have energy above 10 to the power 14, 10 to the 13 electron volt. That's a lot of energy in these small particles, and they are also neutrinos that are extremely difficult to detect. So this is the largest sample we have, and these are shown in the sky, and this is what is called the galactic coordinate system. So the center of our galaxy is here, and this cross and plus signs, they represent which directions the neutrinos are coming from. So there are some uncertainty in the direction of this neutrino. So at this point, so far, we don't know yet exactly which astrophysical objects are producing, for example, the event number 51. Okay? But we try to understand that. Now, if you look at this picture, you can see that there is a concentration of event around the galactic center, and this is something that was first pointed out in a paper that I wrote in 2013. So this is the position of this neutrino arrival direction, and it could be that our own galaxy is producing some of these neutrinos that we detect. So there are some ways to do this calculation that our galaxy can produce these neutrinos. So we have to look into the very energetic supernova at the center of our galaxies, which accelerate cosmic rays, and they interact nearby and produce these neutrinos. And this is one of the first papers I wrote when I moved to South Africa. All right, then we also looked at different kind of source, but in our own galaxy. These are what is called the Fermi Bubbles. And this is a series of paper that we worked on with my collaborators to calculate the neutrinos coming from these Fermi bubbles. And these Fermi bubbles, they are actually some structure in our own galaxy. These are huge gamma ray bubbles detected by this Fermi Gamma Ray Space Telescope. And this is the center of our galaxy. Our sun is here. We are located here. So when we look at towards the center of our galaxy, we can see these gamma ray bubbles if we had gamma ray eyes. So we also looked at possible sources of these neutrinos by correlating them with the direction of the ultra-high energy cosmic rays. So this is the work we recently did with my postdoc, Dr. Maharana, here at UJ. So we looked at the direction of these neutrinos, where they're coming from, and taking into account their uncertainty. And then we looked at the direction of the ultra-high energy cosmic ray with energy greater than 10 to the 20th electron volt. And we found that there are some weak evidence that they may be coming from the same sources, these extremely energetic cosmic rays and very high energy neutrinos. Okay, so I'm towards the end of my presentation. So, okay, so we are the dawn of this neutrino astronomy. So what next? I mean, what can we learn about this with these neutrinos? Well, these high energy neutrinos, they allow a new way to look at the sky that we didn't know before. We could only see the sky with electromagnetic radiation from radio to gamma rays, but now we have another handle and another way to look at the sky. And these high energy neutrinos carry information from the farthest distance in the universe. Photons cannot travel all the way, especially if they're energetic. They cannot travel all the way to the farthest corner of the universe, but neutrinos can, because they only interact very weakly with matter. Neutrinos can also carry information from the dense region of astrophysical sources, which is possible because, again, of this very weak interaction nature of the neutrinos. And it can also identify the sources of ultra-high cosmic rays that I talked about. Now, we can also do astrophysics and physics with the high-energy neutrinos. We can learn about the sources. What is the energetic requirement of the sources to produce these extremely energetic particles? What is the environment of the sources? What processes make very high-energy neutrinos and gamma rays? We detect very high-energy gamma rays as well, but we don't know yet what produces these extremely energetic gamma rays. But if we can detect neutrinos with gamma rays, then we can know about what produces these gamma rays. And we can also probe fundamental interaction at extremely high energies that we cannot achieve on the Earth. All right, we can also learn about the dark matter particles, which constitute the majority of the mass of the universe, and their interactions. And we can also look for new surprises that may come as we look at the sky in a different way that has been done in the past. So the neutrino astronomy also needs to use what we know about the astrophysical sources in electromagnetic wavelengths. So when we combine data from different instruments, different telescopes, then we can get a better picture of what we are looking at. So in that respect, there are already telescopes in South Africa. There Meerkat, which is a pathfinder of the square kilometer array. It's in Karoo in South Africa. There's a Southern African Large Telescope. This is an optical telescope. And we are also a member of this Fermi Gamma Ray Space Telescope. And then there is, of course, the Neutrino Observatory. So combining data from all these different telescopes in different messengers, electromagnetic and neutrinos, then we can get a much better picture of what we see in the sky. And that is what is called now these days multi-messenger astronomy. So look at the universe in different particles, different ways, so we get a better picture. All right, thank you.
Deputy Vice Chancellor Parek, Dean Meyer, ladies and gentlemen, it's really an honor to be here. Choked up. It's beautiful. I had no idea. I had no idea what I was coming for. I thought some ceremony or ritual. What a grand tradition you have. Do it forever. It's absolutely fantastic for you people to get together. I know it might be some work, you know, you have to go out a couple times a year, and especially for the administrators, quite a burden, but oh, how great, how grand. The group gets together, you're a family. It becomes a university, becomes a family. Now I understand why this is here. So it's more than an honor, it's an education, and it is a privilege. And I had this imagination that I was here to give my perspective as a theoretical physicist, but on that account, I have to tell you that we are not normal people. Theoretical physicists are a rather strange bunch. You probably don't really want to know what we think or how we think. But in the way I think about our civilization, I'll tell you, it's just the truth. Physics is 200 years ahead of the civilization of this planet. Physics lives in the future. Physics does not really care very much for the conventions and the ideas of the future, of this present civilization. I've learned what a professor is. I have to admit, some of the things to which I profess are very bizarre. I do not believe in an absolute space or time. I do not believe in an empty vacuum. Empty space is full of the Higgs field and all the other quantum fields. When I see the empty vacuum, it's like a crystal. It's absolutely crystalline out to the end of time. The furthest stars are the same as those here. So the crystal is perfectly uniform, and that's mysterious. You can't see the crystal because you use light and neutrinos. Those are the modes that go right through the crystal. There are so many things that are different if you learn physics than if you stay in ordinary reality. So anyway, we take it for granted that people will not understand us, and then we make our way through difficulty. Now, I realize I have to comment on the science and on the professor being inaugurated. There aren't very many who I would ever say this about, but Professor Razzaque meets Einstein's criteria. What you want in a scientist: imagination, courage, and integrity. 2 out of these, 2 out of 3 are gutsy things. Imagination, Professor Razzaque has it. Courage, keep working and succeeding. It is such a challenge in theoretical physics. Integrity, from the day I met him, this man was as straight as an arrow, has always been the best. Now, that's not ordinarily what I say about other people. We are actually pitiless in our criticism. Why not? It's a tough world. But we have our own standards and our own thing. So what about the science? What would you say? In our business, we'd say, is it good? If it's good, that's as good as you can be. And I would say it is superb science. It is clever science. It is informative, and it is honest. The cleverness is in the neutrino telescope. It wasn't quite explained how clever it is. You can't look into the middle of a galaxy with photons. Photons can't get out. But the neutrinos get out. You can't look across the universe with neutrinos. This was mentioned with photons, but you can with neutrinos. So it is the first innovation in astronomy of any significance since Galileo. Now, the radio telescope came in between. The radio telescope's really good, but the neutrino is the most penetrating particle. It's brilliant. Is it informative? Yes. We're already learning things about the universe using neutrinos that you could not conceivably learn. That's because of the energy range. The energy range of neutrinos is naturally very high. You don't detect low energy neutrinos. So the cleverness and the high energy go together. High energy neutrinos are quite cooperative. They're not so bad. So you can learn things in an energy regime you've never had. You have eyes that see right out to the highest energy possible. Is it honest? Well, I'll tell you this. It's all about the data. This subject is entirely driven by data. It is not driven by any authority. I know the people in this field. I know how the dynamics of this field works, and there is no authority who has any business. If the data says something happens, it happens. And that is honest science, and the data analysis is honest. The data is released to the public. And there are no boundaries. There's no limits. You can ask anything you want. You can challenge anything. Suppose there's a neutral current. Suppose there's this or that charge current. Suppose any technical thing. It's absolutely free for all. Unlimited science. This is what a world-class university wants to participate in. Unlimited, futuristic science that is 200 years already in the future. So I am full of admiration for your university. I'm full of admiration for the science. The candidate, everything is fantastic. I do have, however, a request. First, I was asked to keep this brief, and I will. I'm finishing now. But upon visiting here, I found out we have 54 neutrinos. 54 neutrinos ought to be enough, and I asked the question, is this enough for us to do neutrino tomography, just like tomography in the hospital of the Earth? Can we look through the Earth and weigh the Earth and see the interior of the Earth with the neutrinos we have now? Futuristic, crazy idea. Can we get a number possibly to see if there is a direct measurement with neutrinos of the interior core of the Earth above and beyond the kind of hopeless geophysical measurements we've had for hundreds of years? And Professor Razzaque said, yeah, probably. Matter of fact, yeah, okay, we'll try that. And I'm very excited. So, Schweb, would you please get busy and get done with these parties and tell me if that's possible? Thank you.
Ladies and gentlemen, I'm sure you would agree with me that Professor Razzaque is a worthy recipient of this famed Hall of Fame, the highly prestigious professoriate. I call upon Professor Razzaque now to come forward with the Dean so that we can robe him officially into the professoriate at the University of Johannesburg. Whenever we do this with Prof. May and I and with one of our male colleagues and professors, I said they're often very lucky. They've got two women addressing them.
I was thinking exactly the same.
Okay. Professor Razzaque. Congratulations once again. Ladies and gentlemen, a round of applause.
The University of Johannesburg. Rethink, reinvent.